So we are in 2D case now. Let me start talking about this plane. So I won't talk about cost function right now. So let's say this is W, this is B. Now earlier we had just W, and instead of B here what we had was dependent variable cost function, that was J. Now in this case where will be my cost function? My cost function will be basically this axis, okay, perpendicular to both of them. So you can think of, so you can tilt this plane 90 degrees. So assume that this particular floor is my W and B plane, okay. Now how does my, where does my cost function lie? My cost function is a, so if I start with this plane, my cost function lies at a height, okay. So for example, this example of a plane could be, what could be an example of a plane in this case, where my plane WB plane is this. So basically this is, let's say, direction W, this is, let's say, direction B. Yes, can you give me an example of a cost function? I think ये बात अपन कर चुके थे, right? How was that ball shaped? Right, so we were talking about this. So how does this particular bowl shaped function look like, right? So right, so that's what a bowl means, right? Kadhai, and you extend it to infinity, right? That will have exactly one minima, right? It is convex, has exactly one minima, and is a nice function for us, because if gradient descent or any other algorithm that takes you to minima, it basically means it is the global minima, you do not have to search for anything else. Now as I have said before, as the course progresses, I will keep on dropping this thing that we actually care about minima, okay. But let us start with this. By the way, why do we don't care about minima? Just to state, machine learning people, they care about generalization and not minimization. So let us say there exists a point at which my algorithm generalizes better than at some minima. What would you prefer? Where generalization is better, okay. And these two things always may not coincide. It does not mean that minima implies best generalization, okay. So this is what we are talking about. Now last time I had asked this question about contours. What are contours in this case? I want everybody to be able to visualize the cost function here. Everybody is able to do that? What is the cost function? This is my WB, so this is my WB plane. How many points do I have where I can go on this plane? Infinite, okay. Now W and B can take any real value. For every value of W and B, there will be a corresponding value of cost function J, right? And that will basically give, I mean, that will be the surface, the height of my cost function here. So if my cost function is bowl shaped, you have to tell me what are the contours for it. What are the contours? How do we define contours? Those points where my cost function takes the same value. Can you help me figure out? Concentric circles is what I am hearing. So I will draw a parallel diagram here. So now let us say, so now I am drawing, this is, let us say, B, this is W. Now I am drawing J here. So J, okay. This is my, it is not a parabola anymore, it is a bowl now, Okay. Now tell me, what are the values? The axis of this particular bowl, right, wherever you call the axis, that axis is parallel to J axis here. Okay. In that case, you have to tell me what will be the contours. The axis of this bowl, that means the line that is perpendicular to this particular function at minima, right, passes through, sorry, not passes through, but is parallel to this line. How many of you see what I am trying to avoid by saying this? What I am trying to avoid by saying this is the following. I don't want a cost function like this, right? I am not willing to tilt my kadai. So, I am not talking about such functions. I am talking about functions, okay, right. So, now tell me, concentric circles, right. So, concentric circles will, if I have this one here, but which concentric circles? Parallel to the WB plane, right. So, basically any plane that is parallel to my WB plane is going to cut this particular function, and what will be the locus of this intersection? A circle, okay. And so, what I will get is this circle. This is just one circle, right. Let us say this is this circle, the green one, or maybe I can just draw it in green, this one. Now, if I have let us say another one here, how do I draw it there? Somewhere here, right. How many such circles are possible? Infinite. You can start from this point, keep on expanding, right. You can have infinite such circles. What are the properties of these circles? See, this is which plane? WB plane, right. And as I have said before, we see, if you start thinking of, coming downhill, you will have to assume yourself somewhere here. You will have to assume yourself somewhere here sitting on the cost function. I am saying don't do that. What you do is, you imagine yourself being on this plane where you can walk wherever you want. Okay? The moment you see up, you see the height of the cost function, right. So, wherever you are, if you see perpendicularly this line, wherever you see the cost function, that is the value of cost function. Is this visualization okay? Okay. So, if I am here somewhere, my cost function will have some value here. Okay. So, what is the property of all the points on this green circle? For all points on green circle, I have same cost function value. What about this yellow one? Same value of cost function, but will green and yellow value, will it be same? It won't be same. Here you have J1, here you have J2. So, these two values are different. Now you have to help me figure out how do I do gradient descent here. sorry, value of, right, it attains minima, okay. I am not understanding. You say minima is at 0, 0?
Yeah, it seems like that.
Right. So we are taking the best possible case in geometry. So right now we are assuming that my minima lies here. That's what these. But does it make any difference? You can still keep the same shape, move it somewhere else, right? Such that my minima lies here. But then as we know from coordinate geometry, you can always change the axis such that this guy becomes 0, 0. Okay. So there is no loss of generalization if I say my minima is at 0, 0, at least for this good case. Yes. How do I do gradient descent? So let us say this is the value. It does not have to be on either W or B anymore, it can be some point W, B. So let us say I am here somewhere. So let us say I am somewhere here. How do I go from here to here? This is my only minima. How do I start and do that? By the way, on this bowl shaped function, how do I interpret gradients? What will be my slope? See, for a 1D function, what will you do? Your dy by dx will be same as the slope at that particular point, right? So that line gives you the tangent to this particular function at that point, right? What happens in this case? What happens in case of 3D? I mean, when you have two independent variables? No, my question is, how do I interpret gradients in that case? How do I partial? So if I do partial differentiation, what does that mean? So let's say I do this. What does it mean? Two lines? Two lines? Everybody agrees? So I am leaving circle right now. This, let us say some point here, choose any point on the cylindrical surface, okay, because I do not see anything circular. No, circular, sorry, spherical. I'd like to have that helmet. So see, you have it, okay, it is not bowl shaped, but we care about this curvature, fine. So this is the minima, assume this is the minima. I take any point on this, somewhere here, right? What will be the tangent to this particular surface here? Will it be a line or will it be a plane? A plane means infinite lines are actually tangent to this. So you can't talk about a line being a tangent. What will be tangent to this surface is a plane. Now how do I interpret my gradients? Because in 1D, my dy by dx or dj by dw in this case was actually a tangent to my original curve. In this case, I have a plane. What will be the plane? What will be the slope of this plane? Can you talk about in terms of slope now? You see the problem here? When we were in that is too far. See, when we were in 1D case, I will just this was my j, this was my w, I started from here, dy by dx was actually my dj by w was actually my slope there, okay, and the direction of my derivative here will be my dy by dx is positive, right. So, my update will look like w equal to w minus alpha grad j, and this grad j is positive. So, I will subtract something from w, that means I will come in this direction. Whereas, if I start from here, in that case my dy by dx is negative. So, my update will look like w equal to w plus alpha and the positive part of the gradient, right, because minus and minus will cancel out. So, you will move in this direction. How do I understand this thing in this case now? Where do I want to move? I want to move here, okay. So, this is my goal. How do I reach there? Yes. Now, how many of you know gradients? You must have done this in some calculus, vector calculus, whatever, right? What are gradients? How do you interpret gradients? So, gradients actually give you the direction of the steepest increase of the function, okay. Now, so how do I write the gradients now? That there you have to help me out. How do I write the gradients? So, this will be what? Whatever we are doing in this case, right, it geometrically is generalizable to million dimension, billion dimension, trillion dimension, whatever you prefer, because we can't visualize more than this anyway, okay. So, if somebody says, how do you visualize this in a million dimension? This is what it is, we can't do better. Yes. What does this guy look like? So, it is a vector now, okay. So, my grad j, what will be grad j? Yes. And how will my update equations look like? Let us come to them now. So, until convergence, so repeat those things, until convergence, compute j, compute grad j, and then update. So, let me quickly write here. Until convergence, compute j, compute grad j, and then I will have w equal to w minus alpha right. This is how my training loop looks like. Now, where does this guy fit? Where does this guy fit? How do I fit this vector here now? all I do is I vectorize this, so that's a trivial part. What I do is, this is a vector, alpha, what was here, grad j, right, and grad j looks like right. So you just vectorize this equation. So instead of writing this from now on, we can just write, so we can write this as a W matrix equal to W matrix minus alpha grad j, but we'll come to that later. Right now this equation is sufficient for you. Okay. How do I go from here to here is my question. Note that we are not saying anywhere that I am uphill somewhere, I am descending, I am going towards the minimum. That does not help me. What are the degrees of freedom given to you? You lie only in W and B plane, right? And let's say, of course, you can look up and see what is the height of the cost function. You want to reach to a particular point in this particular floor where value of what is minima? How do we characterize minima? Grad j is 0, right. So if grad j is, I won't be writing this vector other than here. So grad j has to be 0. What does it mean? This partial derivative has to go to 0, at the same time this partial derivative has to go to 0. So both of them have to go to 0 at the same time. Does this happen for our function? It happens, right, because the plane will be like this and this happens. Now my question is, I have some non-zero value of gradient here. What does that mean? Let us try to compute. So let me make my function even simpler. So I have this function now, let's say. I don't want to get rid of this one. So let's say I have this function j equal to w square plus b square. What is this guy? Circle? How many of you say so? Okay. W and B both are independent variables, can take any value from minus infinity to plus infinity. This is what? Ellipse. How many of you go for ellipse? What makes you say so? But the coefficient of both are 1. So if you have to choose between ellipse and circle, it has to be circle. H is 0. So this is that kadai that we are talking about. When W is equal to 0, B equal to 0, what is the value of J? 0, right? So I am here right now. So assume this is my 0, 0 where I am standing. So at this particular place, value of my J is 0. Let's say I move to 1, 1. If I move to 1, 1, what is my value of J? 2. So my height has increased to 2. Which all points will have height 2? Which all points will have height 2? Huh? Circle. Which circle? W square plus B square equal to 2. Right? So I am here at 0, 0. On the same plane there is a circle whose equation is w square plus b square equal to 2. You take any value on this circle, value of cost function is 2. Let's say I move to point root 2 comma root 2. What will be the value of j there? W square, so basically 4, right? Now, where on the same plane w and b I should go so that my value of j is 4 for all the points? Right? So, that circle for which w square plus b square is equal to 4. So, radius is 2, right? Now, what is happening? See, w square plus b square equal to 1, w square plus b square equal to 2, w square plus b square equal to 4. You keep, there are infinite such circles, we have talked about them, okay? And in fact, w square plus b square equal to 0. Right? What is the right hand side giving me? No, under root of that gives me the radius. But what is the right hand side giving me? Value of j. So when I am at 0 comma 0, value of j is 0. When I am at this circle, w square plus b square equal to 1, value of j is, and so on, right? So all my circles where I can move, they still lie on the same plane w and b, they still lie on wb plane. So this point will also lie on one such circle, exactly one such circle, yes or no? Yes. Alright. Now tell me, how do I compute, this is my j, how do I compute grad j? What will be my grad j? This is grad j, मतलब ये भी नहीं कर सकते हो तो, so grad j in this case will be 2w and 2b. So if I am at 0 comma 0, what is my grad j? 0. If I am at, okay, 1 comma 1, what is my grad j? 2. So it's a vector now, right? And so on. How do I interpret this thing? How do I interpret this? Magnitude of? Magnitude of 2. Magnitude of 2 will remain 2. Right. So which vector? Does this vector pass through 0 comma 0? Yes. Right? You put both zeros, it passes through 0 comma 0. So which vectors are we talking about? If I ask you the family, I want you to give me all the vectors of this form, how will they look like? So no matter what wb, whatever I take, the vector passes through 0 comma 0. So this is one such vector. This is one such vector. All these vectors that pass through 0 comma 0 and are perpendicular to these concentric circles, they are represented by this one. Make sure you understand this, right? So for example, what will be my gradient at any point w comma b? What will be my gradient at any point w comma b? 2w 2b, right? And this passes through 0 comma 0. So it does not matter which point you are talking about. The gradient will pass through 0 comma 0. What was the definition of gradient? Direction of the steepest increase in the function. Let's say I am talking about this particular point. I have a bowl shaped function. Which direction gives me the maximum increase in j? Let's say if I go perpendicular to this point, I move infinitesimally, very little perpendicular to this particular vector. How much change do I make in j? No change, right? If I move in some direction like this, right, I had to walk this much, but if I go in this direction, I will have to just walk this much. So which is the direction of the steepest increase in function? Gradient. Geometrically, gradient gives you the steepest, the direction of steepest increase in the function, and negative of it gives you the steepest descent. Which one do we take for gradient descent? We write w equal to w minus alpha grad j. Okay. So if I am here, where do I want to end up? Here. Am I already on the right direction? Yes. Okay. So all I need to care about is I need to reach here somehow. Okay. So is this clear? This geometrical interpretation of gradients. Okay. Any questions on here? Because yes, any questions on this? I can repeat whatever you say in this particular board n number of times, because once I am done with this gradient descent, right, I won't do it for any other thing, because this is the most general thing that we could visualize. Okay. No matter which point you take, if I take point here, which will be the steepest increase? Perpendicular to the concentric circle here, goes in this direction. I go in negative direction of this direction. This passes through my 0 comma 0, which is the minima. All these algorithms that follow this are also called line search, because I am searching for a point on this same line. Okay. And if you see, there is no hill descent here. I am not imagining myself on a hill. I am still on the same plane. I am just moving in the direction that is given by negative of gradient. This, everything that is happening is happening on my WB plane. I am not up on a hill and trying to climb down.
This vector is also on WB plane only.
That's a good question. So where will my grad j lie? On the same plane, right? On the same plane, gradient will have 0 component in j direction. Parallel to what? Anything that lies in WB, right? But parallel से मतलब I can take it out of this plane, you mean? No. Grad J, see, if you see J is a function of W and B, all independent values for this particular J, they are taken in WB plane, not in a plane that is perpendicular, that is parallel to it. They are taken in this plane. Gradient will strictly lie in this plane. Right? Gradient cannot go out of where its parent couldn't go.
मतलब अगर प्लेन पैरेलल है WB के तो उसका जो ग्रेडियंट होगा वो WB प्लेन पे ही लाई करेगा.
Which plane are you talking about?
अगर जैसे बॉल दिया आपने ने.
See, bowl is what? Bowl is the height of bowl at one of these places. You had J equal to W square plus B square, bowl looked in a particular shape. If you take J equal to 2W square plus 2B square, bowl will change. So it depends on this function, but your plane WB does not change. I will still take values from this particular Cartesian coordinate. I think this is a good point to stop. I'll upload all these things